All right, so let's jump into it. So a number of things I want to do today. I want to talk about the homework. I want to go through that in some detail, and not only talk about the questions and the answers, but also look at how we can use MP Lab to, test out our answers and see if our code works the way we want it to. So spend some time going over the homework, and then I want to talk more about writing assembly language. So going into some of the other details on how you can do, in particular, the code for Lab 2, but more generally, assembly language programming issues. I will talk about lab questions and so on. So mostly be a bunch of assembly language going on today. So let me start off. I can go through the homework questions one at a time, but let me start off asking if anybody has any particular questions from the homework that they'd like to talk about.
Could we just go over number 9 on the homework, just for clarification purposes?
Sure. So number 9 is this kind of reverse engineering exercise, right? So we're given the compiled version or the assembled version of instructions, and we're asked to figure out what those instructions were. And let's just pick on the first one, 0x6a00. And a good first step is to turn this into binary, because the patterns that we're going to match against are written out in binary. So the digit 6 corresponds to the 4-bit pattern 0110. Okay, that's just good old binary 6. Remember, A is the number 10, B is 11, C is 12, and so on. So A is the number 10 in decimal, and 10 is an 8 plus a 2. So that's what an A looks like. And then zeros are pretty easy. 0 is just 4 0 bits. So this is 6A00. And then you go to your data sheet, and if you have the quick summary guide, come down here to table 20-1, and so we're looking for 0110 followed by 101, and that pops up right up here at the top, 0110 101, and then it says that pattern should be followed by a bit, which we call A, the access bit, and that should be followed by 8 bits, which we call F, the file register. So if I take this pattern 0110 101, this is A, and then this is F. Okay, this is the actual binary code for the instruction, right, that we're asked to translate into assembly language. This is the template that matches that pattern. And it matches it in particular by letting the access bit, the A bit, be a 0, and letting the F bits be 8 zeros. So go back to your table and look at what this instruction says. It should say clear F, F comma A. Okay, so the opcode is clear F. The operand is F, which is whatever these 8 bits are. Well, those 8 bits are all 0, so this is just clear F0. And then if we weren't ignoring the access bit, we would do a comma 0 for the access bit. But we're ignoring the access bit. So this is just the instruction clear F0. Or if you like being consistent, 0x00. But 0 is just 0.
For the homework, I didn't do that second part. I mean, I only wrote down clear F.
Okay.
But I guess it's so partially got it right.
Yeah, so that's the opcode part, but then the operand is sometimes more interesting. A lot of times the operand will just be 0 or 1 or 92 and so on, but for some of these instructions it'll be more interesting than that. But for the byte-oriented instructions, the file register is usually just the last 8 bits, so it just ends up being that piece right there. So that's not a huge omission for the homework, but yeah, in general going forward, make sure you include both the opcode and the operand.
Well, for the homework, I only included the opcodes, but I guess I'll know that next time.
Yeah. All right, and I've got a message from at least one person saying they're having trouble transferring the files to upload their homework, and I'm not sure what in particular the problem is, what sort of issues, but basically, you know, however you write your file, you want to turn it into a PDF, and yeah, okay, so hold on a sec, let me respond to this person. Alright, and if anybody else is not able to get their homework uploaded through Canvas, email it to me right now. Okay, Canvas closes at 12:15. If I don't have it from you by then, I won't accept it. So if you weren't able to get it to upload through Canvas, just go ahead and email it to me right now. But then let's talk during lab time and make sure that we know how to go through Canvas. And emailing PDF should work pretty well if you have, you know, a weird Apple-specific image format or something. It's possible the mailer will gobble that up. All right. Let me just do this last one because I'm not really sure if I got into any weird ones. But let's just do one more of these. 0x0480. So there's what the digit 0 looks like, there's what 4 looks like, there's an 8, and there's a 0. And so back to our table, we want 4 zeros followed by a 0, 1. That looks right here like a decrement instruction, 0, 0, 0, 0, followed by 0, 1, DA, and then 8 Fs. And this is the instruction decrement F, F, comma D, comma A. So I'm just taking this line from the table, 4 0, 0, 1 DA, 8 Fs, and just translating it over to my paper here. And so this D bit is a 0, the A bit is a 0, and the 8F bits are 80 hex. So this is the instruction decrement file. The operand is whatever the value of F is, which is 80 hex, so 0x80. And then the destination bit is a 0, so I would put a comma 0, and we're ignoring the access bit as usual. So this decrements file register 80, puts the result in W. Now, if the destination bit had been a 1, we could write this as decrement file register hex 80, comma 1. But we can also leave this off, right? If we don't put a comma 0 after our instruction, the assembler treats it as a comma 1. Okay, so the default is comma 1, which means the destination is the file register. But you can always specify it if you want to be explicit. But then every instruction you write, you say comma 1, comma 1, comma 1. It's kind of a pain. So the default is comma 1. If you want the W to be the destination, then you put a comma 0. All right, other questions?
I got a question about like some operands. So the clear F operand, say I type it into a code. So I did that, and then I cleared W register, but then once I go to, how to say, like, add something to the W register, it's as if like the W register wasn't set to 0 but it was deleted. Is it set to 0 or is it deleted? Because I kind of went around that and I just put move LW and set it to 0, and then I was able to add it in.
So can you tell me the instructions you were trying the first time?
Well, so say we're gonna add like a file register, say like num1.
Okay.
So we increment num1, and then move LW 1, so that sets our W register to 1, right?
Right.
And then once we add them together, it's the add LW num1.
Ah.
Then we would get 2 at num1, right?
So almost. So add LW adds a literal value to W.
Okay.
So it's not adding the contents of num1. It's adding whatever num1 is equal to, which is really not meaningful. So I think what you wanted here was add W to a file register num1.
Oh.
Okay, so that will read the contents of num1, and then it'll add the W register's contents, which is 1. That would add a 1 to num1. And either write the result back in num1, or if you said comma 0, write the result into W.
So what about the clearF function? So would it like set something to equal to 0, or would it like delete it?
There's no such thing as deleting, actually. Num1 is a location in memory. There's no way to sort of get rid of the contents of that location or delete them, right? They always contain 1s and 0s. But we can control what the pattern of 1s and 0s is. So clearF writes all 0s into that location. But the location still exists, it still has a value, and so on.
Alright. That clarifies it.
Okay. And that's a really important point to make. In programming in general and in computers in general, right, things don't just disappear. When we talk about stacks, we'll talk about removing something from the stack, but we don't actually delete it. It doesn't vanish, right? Every location in memory has bits associated with it, and we can change them, but if we go back and look at it, it's always going to have some value, even if we haven't put a value in there explicitly. If the first thing in my instruction is copy from, file register 17 to port A, well, it'll read something from 17 and put it into port A. We just don't know what it'll read, but there's something in there, and it'll pull it out and copy it. So literal instructions, they're really useful, but they can get you tangled up, right? Anytime you're using a literal, you're never going to use a file register as an argument, okay, or an operand. It's always an actual number, and that number is the value that's being added or anded or ored or moved and so on and so forth. The other thing to keep in mind is we have sort of 3 types of move instructions. We can say something like move f num1 comma 0, which says take the value of num1 and copy that to the W register. We have a separate instruction, move wf, followed by a file register, which goes in the opposite direction. It says read from the W register and copy to a file register. And then we have this third instruction, which is another move f, if we just say move f num1, and that's the silly one, right? It just takes num1 and it copies it to num1. So those 3 can get tangled up easily. The fourth one is move LW. And when you look at these descriptions, sometimes what you'll see is things like num1 put in brackets, right? meaning the contents of memory location num1, the contents of memory location num1, as opposed to here where we're just reading a value, just a set of ones and zeros, and copying those ones and zeros verbatim, right, literally into wreg. All right, other questions?
Can you go over question 13? I was confused about the EQU statement and creating the symbol time.
Ah, okay. Yeah, and let's talk about EQU in general. We've seen this in the code for the labs, but let's pin down what exactly it does. So, question 13 says use an EQU statement to create a symbol time. File register 88, and then use literals to add 9 to that variable. So EQU is kind of like a number sign define. For what we're going to do, it's no different. So we could say define time to be 0x88. Okay, and that's a C-like syntax, right? But in assembly language, often what we do is we use an EQU statement. So we would say, here's a symbol called time, and we want that to start in column 1. And then we say this symbol is equivalent to hex 88. And now if somewhere in my code I say clear file register time, in the mind of MP Lab it sees clear file register 0x88. Why? Because it sees time as being equivalent to 0x88 because we told it that they were equivalent. So using an EQU statement to create a symbol time is just, time equals hex 88. And then use literals to add 9 to that variable. So how do we add 9 to a file register?
We could do move LW.
Okay. What value should we move into W?
9.
Okay, good. And then what do we do with that?
Add LW.
What do we add to?
Time.
Time. Excellent. One thing to be careful of, right? Literal instructions never deal with file registers. Just like move LW takes an actual number, add LW takes an actual number. So what we really want is add W to file register time. So that'll take W, which is 9, add that to the time register, and now time is time plus 9.
I ran it that way in MP Lab and still ended up with the same result, but is there multiple ways of doing it right?
There are multiple ways, but I think if you add LW time, you're going to change W. It'll change into something probably pretty bizarre. It would actually be equal to 9 plus 88 hex, and then time itself probably wouldn't change. So if you did that in MP Lab, let's take a look at that during lab time, because maybe you were looking at something different from what you thought.
Possibly.
But there are other ways to do this as well. Does anybody see a different way to do this? Set time equal to time plus 9.
Could you do, let's see, time equals hex 88 and then move F time?
Okay, and then
And then add LW 9, hex 9,
and
then move WF time.
cool. So move F time, you probably want a comma 0, right? So what you're trying to do here is copy time to the W register. and then add 9 and then move the W register back to time, that works perfectly well. It's a great solution. Does that make sense to everybody?
Yeah.
So yeah, there's a way to do it using move WF time, provided that W is equal to the new value of time, time plus 9. Those are the two main ways I thought of for doing it. There are always more convoluted ways to do things in assembly language, including incrementing it 9 times, but don't do that. All right, good. Other questions? So opcode's operands, right? The opcode is ENGR, the operand is 40. The opcode is clearF, the operand is 1. The opcode is addWF, the operand is 80. Right? So action and then thing you're doing the action to. Right? Or verb and noun if you like. I'm guessing most people who weren't sure on these already asked me about it, but you know, increment file register 0, decrement file register 0, add 1 to file register 0 but store the result in wreg, that's increment file register 0, comma 0, the comma 0 says write this back into wreg. Copy wreg to file register 10, that's move wf, hex 10. Increment wreg and store the result in file register 10. There's a few ways to do that. One way would be to move wf into file register 10 and then increment file register 10. That doesn't actually increment wreg though. It ends up with the file register 10 being wreg plus 1. But if it's important that we actually increment wreg, let's add literal 1 to w and then move w into file register 10. Write some pic code to increment wreg, store the result back in wreg. So one way to do that is just add LW1, because that's exactly what it does. It increments wreg. But you could also do it using a temporary file register. For example, you could say move wf into location 7f, increment file register 7f, and then 7f gets moved into the W register. That's a 3 instruction way to increment wreg. Add wreg to file register 35 and save the sum back in file register 35. So if you want to add W register to a file, there's one instruction for that: add W to file register. It takes a single operand, which is the file register you want to add W to, and in this form, W plus the contents of location 35 would get written back into file register 35. So that'll do exactly what we want for problem 4. Add W register 35, save the sum back into file register 35. If we wanted the sum to go back into the W register, then we'd say comma 0. Add the W register to itself and store the result in file register 37. So how did anyone do this? Number 5.
I put add WF and then
Ah, tricky. So there's something that I haven't told you yet, which is, well, I might have mentioned it, which is that WREG is actually, it's just a special function register. It's F86, I believe. Nope, it's not F86, it's FE8. It's a file register, right? Anything that we do with any file register, num1, hex 80, we can also do with this register called WREG. And if I look at the contents of WREG, location FE8, right, that's the same as the W register. So if we want to add the W register to itself, we can do something like that, which says take the contents of the W register and add it to this location in memory, which is also the W register. And this would end up with the W register being twice its original value. And you know, if I did a comma 0, it makes no difference. Because without a comma 0, where does the answer get written? Into the W register. With a comma 0, it gets written into the W register. So those would do exactly the same thing. And then you could say move W register into file register hex 37. Without knowing that, you could also have done something like move WF into hex 37. So now this is a copy of the W register, and then add the W register to file register 37. Well, since this is a copy of W, this is adding W to itself, so you're going to get twice the W register, and this is going to store it back in location 37. So either of those would work for question 5. So question 6, write some pic code to add 2 to the file register 88. So some people will just say increment file register 88 twice, and that works fine. And it's actually an efficient way to do this. But then the next question says, what if you want to add 9 to the file register? Hopefully you don't just have to increment 9 times, because that would make our code really cumbersome in general. So, you know, same thing we've been doing, move a 9 into the W register, and then add W to the file register 88. Let me break into some code at this point. And I'm just going to reuse my old code. So let's do this add W register to itself and store the result in file register 37. So I'm going to put an interesting value into W before we do this, right? So I'll put a 17 into the W register. And I'm going to add WREG to itself and store it in location 37. And And so here's one approach that we discussed. And let's go ahead and start running this, and let's watch some variables. So I'll put a watch at location 37. And by the way, down here at the W register entry, if I look at the address, it's telling me its address is FE8, right? So that's how this simulator is showing me the value of WReg. It's looking at this file register location. But we also see the value of WReg up here. It just always shows us what W is equal to. So let's step this once. W is equal to 17 now. That's our interesting value. File register 37 has a 0. That's just the default value. So we're going to move move W into 37. So now location 37 has the value, 23 decimal. And the W register has the value 23 decimal. We're going to add W to the file register 37. W should be unchanged, but location 37 should change to decimal 46. Right, so there you go. So we double W and put it into that location.
Would it also work to do multiply W by 2 and then move it to 37?
Yeah, if you know how to multiply, do you?
I think so. Is it MULLW?
Well, it is. So let's multiply.
MULW.
Yeah, thanks. Let's multiply W by 2. So we'll put our interesting value into W and then multiply by 2.
No, it's LL.
Oh yeah, multiply literal by W. Okay.
Oh, yeah, okay.
So let's go ahead and run that, and let's look at our variables. So W is equal to 37. Let's multiply it by 2. So we'll execute that multiply instruction, and W hasn't changed. I don't feel like that actually executed. So that's perhaps unexpected. It did multiply it, but the result does not go back into W. So let's take another look at our data sheet, and let's go to the full data sheet. So multiply literal with W, and it tells you W times that constant goes into product H colon product L. So multiply is a funny instruction. It's the one instruction that does not put the result back into the file register or into W. Because multiplying two 8-bit numbers theoretically gives you a 16-bit answer, and you couldn't fit a 16-bit answer in W or in, a file register. So there's a pair of special registers called product high and product low, and those hold the result of your multiplication. So we can add another watch down here, product L, and hey, there's our 46. So after we do this multiply by 2, we could say something like move FF product L into hex 37. So let's go ahead and run this. So W is equal to 17. We're do our multiply, and location 37 still hasn't changed, but now we move product L to 37, and there's your 2 times W. So yeah, multiply is yet another way to do this. So let's see. Question: do product H and L only hold the results of multiplication, or do they hold any 16-bit numbers in general? You should be able to load any value into there that you want. But let's see. Now let me go to my short data sheet. They don't tell us if they're read write or read only. So my favorite answer in programming courses, let's find out. Let's see if we can store arbitrary values in prod H and L. And let me add prod H to our watch list. And let's just load some values into W and push that into prod H and prod L, and let's see if it takes. So we'll build this up. We'll run our simulation. We'll single step looking at our variables. So I've got a BE into the W register. Can I push that into prod L or prod H? Yes, I can. And then EF goes into W, and I can push that into product L. So at least according to MPLAB Simulator, it looks like the answer is yes, we can use these as general holding places for a 16-bit number. Whether that actually works in the chip is not guaranteed just because it works in the simulation, but as far as I know, you can. And it's an interesting question in general. Are these special function registers generally available? Some of them are, right? Product H, product L, probably pretty safe. But some of them, you know, like port A, we know that's not generally available because that's connected to the I/O pins. Some of them, like timer 1 con, right, might be safe to use, but setting values in here interacts with hardware inside the system. Some of these, like the interrupt ones, intcon 0, intcon 1, and so on, those are definitely not generally available. They actually have very specific meanings. Alright, use literals to add 9 to WREGs. It's just an add LW9, add 9 to file register 88. So if you want to do that with a literal, you know, move 9 into W with a move LW, and then add WF to 88. Or put 88 into W, add LW9, and then put W back into 88. We did the EQU statement for time, use literals to increment file register 40, so again, move a 1 into W and then add it to 40, or put 40 into W, add literal 1, push it back. Subtract 1 from 40, that's just subtract LW. Well, actually there was a there's a detail in here. So subtract WF subtracts the W register from F. So suppose we want to decrement file register 40. One way to do that is put a 1 into W and then subtract W from file register 40. Okay, that will work fine. It's tempting to do the following also. Move F into the W register, subtract LW1, and then move W back into file register 40. And this actually does not work. So let's mess with this for a minute and get rid of this. Let's look at file register 40 and let's give it an interesting value like I don't know, 100. So let's decrement file register 40. Move LW1 sub WF 40. That's my Thursday garbage truck. They won't be here long. So I'm going to initialize file register 40 to be 100, just so it's something interesting to decrement. So I'm going to move a 1 into the W register, and if I step that instruction, W register is equal to 1. And now I subtract W register from file register 40, and if I do that, file register 40 goes to 99. That worked perfectly fine. But there's a different way you might try to do this. Which is to first copy file register 40 into the W register. And then subtract 1 from the W register, and then move the W register back to file register 40. And let's go ahead and start running this. Let me reset location 40 to 100. Alright, so we're going to copy file register 40 into the W register. There we go, W is equal to 100. Now we're going to subtract 1 from the W register. And guess what? The W register changed to 157. What's up with that? And now when we copy that into location 40, we did not decrement register 40, we actually added 57 to it. Okay, and this will trip you up all kinds of ways if you don't know what's going on. So the simulator here helps you see what's going on. And 1 is a literal, but this is just an annoying thing that we have to live with the PIC processor. If you look at the description of sub LW, it says subtract the W register from the literal. So sub LW1 is actually saying take 1 and subtract the W register and copy that to the W register. Even though sub LW sounds like subtract 1, it's actually subtracting the W register from 1. So W register was 100, we subtracted 1 minus 100 is minus 99, that's 157 in 2's complement. So this is to me kind of annoying, but it's just something we live with. Let's see if we can get super duper fancy. Let's try negating file register 40 after we're all done. Let's start running. Let's look at our variables. Let's put our interesting, if I need to go back and rerun it. Put our interesting value into location 40. Alright, so we'll copy 40 to the W register. We'll subtract the W register from 1, which gives us 1 minus 100, which is supposed to be minus 99, but it shows up as 157. And then we copy that to location 40, so now location 40 is 157. But now let's say negate that file register. In other words, take negative the contents of that, right, using 2's complement. That gives us back to 99. This is setting location 40 to 1 minus the contents of file register 40. When we do this, we're setting file register 40 to the negative of 1 minus 0x40, which is negative 1 plus 0x40, which is 0x40 minus 1. It's good old algebra.
Would it be possible to use the add opcode and add -1?
Yes. And that's exactly the answer for number 17. Is there a way to subtract 1 without using decrement or a subtract instruction? You can add -1. That's the same as subtracting 1. Awesome. So here's a third way to do this. With one possible wrinkle. Let's see what happens when we try to move -1. Actually, maybe it works. I expected that to give us an error. Oh, that actually works. Cool. Okay, so it changed this -1 into 0xff, which is how we write -1 using 2's complement as an 8-bit number. So so this should work automatically. So let's start executing it. And let's look at our variables. So first thing we're going to do is move a -1 into the W register. So there's our FF. And let's make location 40 interesting. And so we'll add W to file register 40. And that will change it into a 99. So that works just as well. And takes a lot fewer instructions. All right. Any other questions on that homework?
I'm all set.
Okay.
This is really confused me about the due dates, actually. They say they're at 12 p.m., but I'm confused if that's noon or night.
12 p.m. is noon,
Okay.
which I think I mentioned the first class.
Oh, I must have thought.
All right, and the labs also, they're due at 12 usually. All right, other questions? All right, let's take a 5-minute break, and then I want to come back. I want to talk about some more general things related to MP Lab and assembly language, and then I want to show you a fun tool you can play with to further help you debug your code. So let's pause for about 5 minutes, and we'll come back. We'll jump into some more stuff.